All right, in this screencast, we're going to start chapter 4. And guess what? Carbon is awesome too. Uh, Maybe not as awesome as water. So water is like awesomer than carbon. But carbon is still pretty awesome. So let's see why. All right, carbon is our backbone of life. Okay, living organisms consist mainly of carbon-based compounds. Okay, carbon is unparalleled, and that's completely it's really unrivaled, and that's why we're made of mostly carbon. In its ability to form very large, very complex, and diverse molecules. Okay, so this one simple element can form such a wide variety of the molecules that make up life. Okay, those molecules are proteins, DNAs, carbohydrates, lipids. All of those molecules that distinguish living matter are all composed of complex carbon compounds. All right, study of compounds that contain carbon is organic chemistry. Didn't know you were going to get some more go, did you? So organic compounds can range from very small, simple molecules to ginormous, incredibly complex molecules, colossal even. And it's this diversity, this very wide variety that allows the diversity of carbon that allows all these variety of molecules to exist. Most organic compounds, we all know they contain carbon. Most of them also contain hydrogen. Okay, and when you put carbon and hydrogen together, you get something called, there's a slide later, but I might as well name it now, a hydrocarbon. So a hydrocarbon is a compound that contains hydrogen and carbon. It's that simple. Scientists are not clever. We name everything for what it is and or what it does. All right, so let's look at how, at some point life evolved. We'll talk about that in the spring more, but in order for life to occur, the organic molecules that make us up had to exist. And so Stanley Miller is this guy who did this classic experiment. And whenever you see the words classic experiment, you have to think to yourself, this is something I need to know. Classic experiments. We're going to do all the classic experiments. But Miller demonstrated the synthesis of organic compounds under abiotic conditions, so conditions that are not living. So going from no life and making organic compounds that can then become life. So we knew kind of the things that were in the atmosphere and available on Earth before there was life. And this guy wanted to see if he could mix these things up and make them into organic molecules. So abiotic synthesis, so abiotic means not living, of organic compounds, perhaps near volcanoes or deep sea vents, had to have been essential for this. Okay, and this is the Miller experiment. It's often called the Miller-Urey experiment as well. Make sure you can recognize this apparatus. So we put all the stuff that was in the atmosphere. It was a very, very stormy time way back then. So we put some electricity through our atmosphere containing compounds like methane. This is ammonia. The 3 is supposed to be by the nitrogen, hydrogen. These were all present in the early atmosphere. And put some electricity through it, bazinga, run it through a condenser, which cools it off, and then drip, 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 and you get some C here, and the water contains organic molecules. Okay, so it could happen. It may not have happened exactly like this, but we can make it happen. All right, so now we have our carbon compounds, or our organic compounds. Let's learn why carbon, and why carbon is so awesome. And it's so awesome because chemistry, it has a valence of 4. So its electron configuration is the key to atom's characteristics. Okay, electron configuration determines the kind and number of bond an atom will form with other atoms. Okay, and because carbon is unique in having, I know it's not the only element that has a valence of 4, duh, but it is the one that is the most adept at it. Okay. The ones further down in group 4 get a little persnickety and snobby. Okay, so it can bond with up to 4 different atoms at a time. So let's look at a little bit of that. Because of the 4 valence electrons, it can form 4 covalent bonds with all the same atom, a variety of atoms. And because of this, it can make these large, complex molecules that are organic molecules for life. So if you have a molecule with multiple carbons, so the carbon bonds to 4 other atoms and has a tetrahedral shape. Oh, there's our Vesper. Ba-bum. If you have 2 carbon atoms joined by a double bond, okay, it's going to be more flat. And here we go. So here we have methane, carbon bonded to 4 other atoms. You're going to get this tetrahedral shape right here. If you have 2 carbons, it's going to form this like 2 little tetrahedrals here. I'm just making a mess. Let's take that stuff out. Too confusing. And then if you have a double bond here, you'll see it becomes flat. It'll be in the same plane as the carbons. And so we have our name, our molecular formula, which is CH4, C2H6, C2H4, and then our structural formula. So this is more kind of like the Lewis structure formula, very simple. Ball and stick model is our Vesper. Space filling model, I suppose these kind of both Vesper. All right, so just kind of keep that chart is a good thing to just keep in mind. The electron configuration of carbon gives it covalent compatibility with many, many elements. But there are a few elements that it seems to be selective for that are involved in these organic compounds that make up living systems. And these other elements are hydrogen, oxygen, and nitrogen. Okay? And these guys get together way more often than any others with carbon and form our living molecules. So let's look here. And so hydrogen has a valence of 1. So you would have 4 hydrogens per 1 carbon. Oxygen has a valence of 2. Okay, you can get 2 oxygens onto a carbon. Nitrogen has a valence of 3. We can get at least 1 onto carbon, and then here's carbon with our valence of 4. Okay, so learn these. These are the elements present in organic compounds. Elements present in organic. Really, my handwriting is atrocious. Well, it's good you learned this now. Present in organic compounds, okay? And we learn our phrase is they're not in the right order, but it's chons or chon. The S will come later. Sulfur and phosphorus is also present as well in some organic compounds. But these guys, chon, they are the main ones. Okay, so now how do we get all of these incredibly variety of organic molecules? We look at the carbon skeleton. So how the carbons are bonded to each other in an organic compound, okay? And so carbon chains form these long rows of carbon that branch or bend or twist or circularize, and we call this the carbon skeleton, like the bones of your body. Carbon chains can vary in length and shape. Let's look at a few. So here they vary in length. You can have 2 carbons, 3 carbons, 10 carbons, 100 carbons in a straight line. They can branch. You can have just a straight line here of carbons here with butane, or you can have a branch of carbon chains with 2-methylpropylene. And like this, the series of carbons, how the carbons connect to each other, that's called the backbone or the skeleton, carbon skeleton. They also vary in double bond position. You can get one here or one here. And we'll look at these. Oh, that is not what I meant to do. Or the presence of rings. Carbons can circularize and form rings like cyclohexane or benzene or all that kind of good stuff. So you can see how, you start to see how, as you increase the number of carbons, they can get to be some pretty complex and diverse shapes. All right, as I said before, hydrocarbons are organic molecules that contain carbon and hydrogen. These molecules we're going to talk about more in chapter 5. These are our fats and lipids. And hydrocarbons can undergo reactions that release a very large amount of energy. So a very large amount of energy stored in our fats, or in our hydrocarbons. Here's a picture of a fat. And you can see, remember, the black is carbon, the white is hydrogen, and the red is oxygen. So there's just a little oxygen, but lots of hydrogen and carbon. And this is what a fat looks like, ball and stick. And this is what a fat looks like in your cells. Yummy. All right, the last thing I want to talk about in our little organic chemistry chapter are isomers. So isomers are compounds that have the same molecular formula, but different molecular structures, okay? So different structures and different properties, okay? So structural isomers have different covalent arrangements of their atoms. There's cis-trans isomers that have the same covalent bonds, but differ in how they're arranged in space, and enantiomers, which are mirror images. So let's look at what these guys look like. So here's structural isomers. 1, 2, 3, 4, 5. So these both have a structural formula of C5H12, I think. 2, 4, 6, 8, 10, 12. Yes. So these are both C5H12, but how they are arranged is different. This is a straight chain. This is a branching chain. Okay. You can have cis-trans isomers. Okay. So cis is when things are on, when your two functional groups are on the same side. That's called a cis isomer. Trans are when your functional groups are on different sides of the plane. Okay. Again, same formula, different structure. Okay. And enantiomers, again, same formula, but they're mirror images of each other. So if you put up your two hands, your left and right hand here, and hold them next to each other, they're mirror images. And that's how enantiomers work. And enantiomers are really valuable in pharmaceutical industry. So you can have two enantiomers of a drug, and they can have significantly different effects. Usually one is like a placebo, it does nothing. And the other one does super fancy stuff. Okay, so let's look at a couple. So here, ibuprofen, all right? So we all take ibuprofen when we hurt ourselves or have a headache or something like that. So the ibuprofen we take is S-ibuprofen. This is active. If you take our ibuprofen, which you see as a mirror image, pretend this is the mirror, it does nothing. Okay. Same thing with albuterol, treats asthma. The R-albuterol is the effective enantiomer, and the S-albuterol is the not so effective one. Okay. So those are all kind of important things for carbon. And again, carbon equals good.